Good afternoon, everybody, and welcome to University of Manitoba. I'll start with my talk with some introductory material on robotics, where it's coming from, where the word robot is coming from, and some history of application of robots in conventional sense. Then after that, I've collected a bunch of video clips and pictures describing new applications of robotics in various areas. And I would like actually to conclude my talk with some of my thoughts of what I see robotics will go in near future. So Dr. Jayas gave a very good introduction about the term robots, and I'm going to reiterate what he has said a little bit faster. I will go through that. Actually, the word robot is coming from a Czech word called robota, and robota means forced labor or work. It was never used as a robot to replace the name of artificial workers. So what happens actually, in 1920, a person called Karl Čapek, who is a playwright, decided to write a play describing artificial workers to work in houses and help people. And he didn't know what they called them. So he was struggling, and his brother Joseph is a painter. So Joseph was painting at home, doing some drawing and painting, and then Carl came to him and he said, well, Joseph, I want to write something about this play, and I don't know what to call these artificial workers. I was thinking of calling them labori, but in my opinion, it's very bookish. What do I call them? So Joseph came back to Carl and he said, well, call them robot. And then he kept on painting. So that's how you know this name attached to what we call it artificial workers. In 1921, Rasum's Universal Robot played in Prague in 1921. This is the only picture remained from that play. And as you can see, the right three people are actually robots that serving their masters. They have their own intelligence to a certain extent, but simple, and are very happy to serve. You have read Isaac Asimov's stories on robots. He's the first one who introduced the term robotics, and in 1950 introduced a series of books called I, Robot. And in those books, he introduce robots as creatures that are there to help and protect some humanity. In 5 years, Hollywood version of the same iRobot was introduced by people in Hollywood. You will see very similarity with the picture in this by Isaac Asimov's book and the Hollywood advertising of that thing. There are some dissimilarities as well. You will see that this robot, the Hollywood version, is kind of a Tom Cruise version of the robot, holding probably Nicole Kidman and saving it. Laws of robotics. Asimov in his book came up with 3 laws which he felt that is necessary in order to have robots work in harmony with people. Have you seen the movie I, Robot? Will Smith played. And those laws are actually taken from Asimov's book. Each law supersedes the other one. You cannot do law 2 unless you be sure law 1 is satisfied. And law 1 says that do not injure a human being. Throughout his story, Asimov decided that he needs to add another law, law 0, which looks at the human being or humanity collectively. And it says that we have to be sure that we don't injure or harm humanity. Definition of a robot. Since 1960, there are so many robots developed and manufactured by different countries and were used. So every country came up with their own numbers, that we have so many robots, our robots are more than yours, et cetera, et cetera. So Robot Institute of America came up with a definition for statistical purpose. This definition is very dry and mechanical. It talks about manipulators that can move material, part, tools, and they can be programmed to do certain motions or performance. If you open dictionaries, every dictionary have different definition for the robots. The one I like, and I think that some researchers also agree with me, is this definition that robots are electromechanical systems that do two things, two characteristics. The first thing is that they interact with the environment and they manipulate the environment. And the second thing, they have a certain intelligence, degree of intelligence. They can actually make choices. I'm not saying they decide or make decisions, they make choices on that one. You need to be sure that robots, when you define something as a robot, you be sure that the robot is not natural. So an insect, we cannot call them robot. The robot should be artificially created. You have to be sure that robots have certain intent or agency, and I will discuss this one a little bit more on that one. What do we mean by intent and agency? The definition of an agency that I found out is called aim and power. So any system that can give you this impression that there is an aim and there is a power inherent to that machine, then to a certain extent you can relate it to robotics. You can define the agency into two parts, mental agency. The car you see on the right-hand side looks like a car. It's been actually taken from the movie science fiction television series. It's called Night Riders. You have probably seen that one. It's a Pontiac, and they build it with the intention that this car ultimately is going to talk and communicate and make decisions for the drivers. And actually it's doing it in this series. In that sense, this car has what we call it mental agency. It has the ability to make choices and make decisions. So therefore, it can be called a robot, although it does not look like a robot. Physical agency is the one that we are very familiar with that. By physical agency, we mean that the robot should look like kind of an anthropomorphic, look like human being, or zoomorphic, look like animals. The example of the anthropomorphic robot is this biped robot called Asimov, developed by Honda. Asimov actually is coming from advanced step in innovative mobility. It has a leg of, it's about 4 feet high and 120 pounds. And recently they showed that it can actually run at about 6 kilometers per hour. Definitely faster than I do for my jogging, which is a little bit disappointing, but that's the way it is. And as I'm getting slower and slower in my exercise, this guy is getting faster and faster. So this is also disappointing. Asimo in Japanese is pronounced ashimo, which happens to mean legs. And another example of the zoomorphic robot is this Abo, which is a robotic pet, which again in Japanese it happens to mean companion. And it's meant for that. It can talk, it can see, it can recognize some commands, verbal commands, and it has the capability to mature over time by interaction with the people or other Abos. This one has been made by Sony. Now, the first truly modern robot which has been used in industry has been created by two people, an entrepreneur and an engineer, George DeWall and Engelberger, who actually decided to build the first Unimate robot. And this first Unimate robot was built in 1960 and was sold to General Motors and installed in one of their factories in 1961. It looks like this. It looks like a boom. It can retract and track and go back and forth. It can go up and down, and it can swing. And by the way, our university has one of these robots, which was donated by the CN and is still functional and is darn good. Robotics have been applied extensively in factory for car manufacturing especially. This is a new development in Germany. This is a transparent factory made built in Germany to build cars. In this transparent factory, as is obvious from its title, the cars can be seen from outside, and you can see how your car is being manufactured. So all you have to do is to order your car, the color, the brand, the model, and what options you want. They are going to deliver the parts, 1,200 parts and 34 pre-assembled components to this factory. And as the car is being assembled, you can see how it works. As you can see, this factory is quite clean. The surface is very, very clean because most of the dirty and oily parts, such as jobs, such as assembly, painting, and everything is done for another place. This place is only meant for putting things together. Benefits that so far we have gained by having industrial robots in the factory is that we free the workers from doing a dirty, dull, or hazardous job. We move them actually to a higher level. We replace them with robots. Is this bad? Not at all. Are we going to create unemployment? Not at all. Those workers that used to do heavy labor and dangerous job are now working towards designing a robot, towards installing those robots, towards programming those robots, and maintenance of those robots. So we are progressing in that aspect as well. So I'm going to move you off the factory floor. These are the things that you have seen previously, probably. And I'm going to show you some pictures and some video clips. Hopefully, they are going to work on this computer. We tried that, it worked, huh? And we'll see where we go from there. I'm going to discuss a little bit about the application of robotics in healthcare. Everybody can get sick or requires attention by a doctor. The most feasible and desirable way to communicate with the doctor is eye to eye and person to person. You would like the doctor to touch you, to examine you by his own hand. You want the doctor right away to explain to you and discuss it with you. In this case, this doctor actually is performing ultrasound diagnosis on the abdomen of a patient. Ultrasound is a probe that they can put it over the abdomen. The ultrasound wave travels through the body and reflects back, and it creates an image of internal organ for the diagnosis system. That's the ideal case. But what happens that you are in northern Manitoba and you don't have direct access to a specialist? You get abdominal pain. You don't know whether it's appendicitis or it's a simple abdominal pain. The nurse can do her best or his best to help you, but there is a limitations that she or he can do. So what they do, they have to refer you to a specialist, and they have to fly you, likely, to a nearest hospital, and the specialist has to do certain diagnosis. Imagine that you are in a space, and the same thing is happening. And this is not unusual. So what do? You carry an emergency crew to the space, stay there for emergency cases? Not really, that's not feasible. So the alternative solution to that ideal case would be to have doctors on call in different locations and are specialists. And then at your location, you can have a system consisting of a video, of audio-video instruments, and a robotic arm that can perform ultimately the certain tasks that your doctor would do. So in that case, you don't have to move somewhere. The doctor will examine you and will tell you the results or the urgency of the case. Here at University of Manitoba, we have developed our first tele-ultrasound robotic system. It's comparable with what French people did in France and also Japanese. Here you will see that the patient is lying here in bed, and he's not communicating with the technologist or an expert system in that area, whereas the robot is actually performing some diagnostics on this patient. What you see on the right-hand side is the ultrasound technologist from the Health Science Center who is performing the ultrasound diagnosis. He's not touching the patient, and he can be far, far, far from the patient. He's not even looking at the patient. He's actually looking at the ultrasound images. We showed for the first time that, yes, with this system, With this system, we can perform ultrasound diagnostics remotely. And we showed that it's possible to capture the images of the heart, a very dynamic system. So that could be the first step. And hopefully what we expect to see is that we would like to see this system up and running somewhere in northern Manitoba when there is not much access to specialists. So everybody will have equal access to specialists. Here there are images that the robotic arm captured for us, and those images are meaningful. Robots have been used in many other applications. In brain surgery, in bone surgery, these robots have been used. Here at Pittsburgh Shadyside Hospital, these doctors actually introducing how this robot can be used in order to hold the leg of a patient. And by the way, this is not a patient, and was not a patient as well, okay? Just wanted to remind you of that. And this robot actually performs some drilling. The accuracy far greater than a surgeon with his own hand can do. And therefore, the doctor can then apply those implants into the cavity that was drilled by the robot. Rehabilitation robots. In Korea Institute of Science and Technology, they have developed robots that look like a sleeve and you can vary it. For those people who have a little bit limitations in their movement of hand and they require constant rehabilitation or push, this robot can work. The actuators are pneumatic. Pneumatic is quite clean. It works by air and you can get it from everywhere. You can make prostheses. Here, and for amputee. And I'll show this picture, and I'm not going to talk about it because it's self-explanatory.
My electric arm has been a godsend to me. It has made me a whole person. Just Phyllis again.
Okay. So you see the smile on this woman saying that he has his life back again, and that is very important. Here at the University of Manitoba, we have developed our first humanoid arm that is meant to look like the arm, to act like the arm, and basically work as a replacement for the arm, either prosthesis or mainly for some interactions with humans as well. The arm actually has 7 degrees of freedom, and here we are showing the dexterity, the manipulability of this robotic arm. As opposed to other researchers, this robot arm is pneumatically actuated. And pneumatic, as I said, is quite clean, so can be used in hospitals as well. Somebody suggested to take one of these robots, send it to China for Olympic. So we are among the Canadian, moving the flag. So we are still working on that one. I'm not sure whether this robot needs a visa to go there or not, but we'll see. A full version of a humanoid robot was built by Sarcos, is a company. Sarcos means flesh. And the idea is that to duplicate the human motions in terms of the speed and smoothness. This is an important area. If we can duplicate human motion in smoothness and speed, then we can actually have a robot to be placed of the person in very hazardous area. So without saying more, I'm going to show you this video. Okay. So if you had one of these robots, at home, and if you get bored, what do we do with that? Say, let's dance, huh? But they're very, very expensive. I don't think we can ever afford one of them in each of us, our home. However, the technology that they have developed by Sarkos has been used in many other industries, and that is of value. Let's move you from this healthcare to exploration, subsea exploration, space exploration, and they all have a certain characteristic. The environment is hazardous. The environment may not be good for the human to operate there, but robots can produce far better results. On the other hand, you cannot let the robot to be autonomous over there, because anything can go wrong, will go wrong, and robots nowadays do not have that intelligence to decide and act completely and recognize everything. So what you do, you combine the intelligence of the person, operator, and the strength of the robot, and combine them and create what we call it a tele-manipulator, or in this case, master-slave arm. I'm going to show you a video of this master-slave arm that we have it at the University of Manitoba here. In this case, the master arm is this arm, which is held by this researcher here. And the slave arm is the actual arm that you can place it outer space or in deep sea. The motion of the master is transmitted decided by this researcher, and then it's going to be transferred to this robot. So the robot is supposed to follow that one. So what is it that we gain from here? The robot can be in a very, very hazardous area. It could be deep sea, and the person could be in the ventilated room up in the ship, and controlling this robot. Good. So now we know that robots and human can work together in order to perform a certain tasks. Here we made the task a little bit more difficult. We asked this robot actually to do the inspection without hurting, anybody. So we put this picture here, and we tried actually the robot to go as close as possible to this person or this figure without actually penetrating into that face. That has been done through two things. One, the manipulation of this master arm that is coordinated by the human, but at the same time, we put what we call it a virtual wall in front of this master arm, and as soon as the master arm feels that virtual wall, produces a force here to the hand of the operator, saying that, no, you cannot go further. Even if you want to go and penetrate, I'm not going to allow you to do that. So you will see, thanks to the technology, the human-robot interaction with the environment becomes more and more advanced. So far we talked about when human and robots are working together, but they are far from each other. We have another concept that human and robot can work together at the same time, at the same place, so they can feel each other. Human can push this robot to do a certain task, and the robot at the same time can produce a certain strength and give a signal back to the robot. This is the concept of power extender. I'm going to show this video to you, and then you probably will know what this system is. Do you know what it is? Does it remind you of anything? Wheelbarrow, okay? Wheelbarrow sometimes can be difficult to push, but with this system actually, the guy can actually move. So the pushing is called by that wheelbarrow. You can see this wheelbarrow is a little bit not tame, is pushing the person forward. This goes back to many, many years ago. We are looking probably 30 years or so from now, before. Now I'm going to show this power extender with this video, and it's very self-explanatory, so I'm not going to talk.
Wires, motors, and computers, this would just be 400 pounds of metal. But with them, this massive arm, built by students of the University of California, Berkeley, is powered by a huge compressor hidden behind the curtain. Even on my first try, I could move it easily, as if it weighed 10 or 20 pounds. My own arm movements are picked up by sensors in the ring around my forearm, then translated via a computer into movements of the mechanical arm. A simple gripper opens and closes the hand.
So the same concept in 2004 was introduced again from University of Berkeley in this exoskeleton form. You can consider this one as another person, human being, which is attached to the first one, and all it does is follow the second person, but any load is going to hold it. So imagine two people are side to side. The first person decides to move and the second person follows it, but the second person carries the load. So this load is carried by this second person, by a mechanical second person. A very, very useful things in factories and in airports, in warehouses, and etc. Ultimately, we would like to see our robots to be autonomous and have their own decision making. This is the robot with 2 arms and with the torso made in MIT Humanoid Robotics lab. This one shows that this robot does not need human to be there, and it can recognize the can. It can hold the can, move the can, and all those kind of stuff. When you deal with a robot that requires certain intelligence, there are 3 things you have to pay attention. One of them is sense, think, and act. The sense, think, and act cycle is very, very important. And amongst those, sensing is known to be the most challenging task in robotics. We are moving to the area of mobility. Once you have your robots, you need to make it mobile. Mobility can be done simply by wheels, but wheeled robots are no longer that much attractive because of limited mobility they have. The world is 3-dimensional. So there are so much work done on mobile robots. And this one is done by Boston Dynamics. And I believe that McGill University has also been contributing to this development. This looks like a 6-legged machine. Each leg basically operates on its own, but somehow they coordinate with each other at a little bit lower level. You will see that collectively they produce an intelligence that intelligence does not make them survive in every harsh environment. It can actually walk over the rocks without collapsing, or it can survive even it collapses it. So I'm going to let this one go to a certain extent because there are some parts that you need to know. It's extremely interesting to see that sometimes small ideas, how they can push the technology. And this one jumps in the water, and you can actually do it. From 600 meters, you can actually control this robot. And it does backward swimming as well. That's interesting. This version I wanted to show you to give credit to McGill University that they built that one. And this one does the same thing, and it can rotate and swim and all those fancy stuff that you like to see. We get inspiration from nature a lot in order to develop robotic system. This guy is a gecko, and people were very interested in knowing how this gecko moves. By the way, this gecko is living in Winnipeg here, and this picture was taken by one of my students who wanted to study this gecko's movement. When we do this, after that, people model this system. And after that, they developed that one. This one is a gecko version developed at MIT, Carnegie Mellon University, Nano-robotics. The main interesting things here is that this robot can actually stick to the wall, vertical wall, and move up and down. The technology they use is yeah, I'm not sure whether I can show this one or not. The technology they use is they looked at the foot of the gecko, which has billions of hair, and those hairs actually can bend and can produce a surface traction with any kind of surface, including glass, with no adhesive anything. That's called a dry adhesive technology. You can actually get inspiration from the fish. This is done at the University of Berkeley, and it's a fish, artificial fish that can produce a very, very nice natural swimming. Initially, when I look at this fish, I thought that it's a real fish, and they put a cap or a can over the fish, and the fish struggles to get out. But that's not true. That tail is artificial, and you will see how natural it is. This interesting quadruped robot is done by Boston Dynamics. You know, one of the issues is carrying the load. Imagine you are in another planet which has a high gravity, and you want to carry the load, not the astronauts. So in that case, you need something like this guy, which they call it Big Dog, which can carry up to 120 pounds on a 35 slope. Everything is centralized. I want you to pay attention to this guy. This guy who kicked the dog is not a psycho, he's a scientist. He is actually examining the stability of this system, which is an interesting and challenging problem. The last thing you want to do is that you fly one of these stuff to orbit or to another planet, and after 1 minute, this guy rolls over. Who is going to pick it up? You don't want that to happen. The last biped robot that I wanted to talk about is biped. You know, one of the interesting things is that how human walks so effectively and so efficiently without any energy consumptions. So here researchers at University of Manitoba studying as similar to other universities this biped robot, and they try to examine how the natural walking is happening. They can show that there exists a certain class of robots that, given a certain condition, it can naturally use its own energy without applying any energy and walk, except for this case. Bad things can happen, huh? Nano-swimming, which I will not go much into details, you know, when you look at the small scale at the nano level, there are two things that you have to be careful, is that how are you going to miniaturize the actuators and the power sources? These are the two things that in a meeting 10 years ago, one of the researchers said, power sources is also important. Now today we just talk about these actuators. Actuators, you cannot be able to make it small, but you can use a bioactuators. Here what they did, they attach bacterias, real bacterias, to a polymer disc, and then they glued this polymer disc to the head of this robot. And that robot can deliver drug or medications, you know, to a certain area of the body. Now, each of these bacteria, they have their own certain of movements. They have this cork-sized tail that rotates at 300 hertz. And by doing that one, they push themselves forward or backward. So if you have a bunch of those bacteria, as soon as you attach them here, this bacteria starts to move, and they can actually push this robot different places. Now, but you have to have some means in order to turn them off and on. And they do it by injecting some chemicals. By certain chemicals, I guess copper something, they can actually disable these cork-sized tails, and they become disabled or dormant. And then when they inject another chemical, they start to become active. So you can actually put them in drops of different blood, for example, and then move them different places. We, as I said, be inspired from nature a lot. And we know that our body is quite efficient. And we know that our actuators are muscles. So here at Festo, they try to develop, and I will show you, oops. They try to develop what we call it muscle-like actuators, that you can apply here a certain pressure, and these guys move up when you apply a certain pressure, and they can move down when you release the pressure. They look exactly like the muscle. And then they have shown that these kind of muscle can be used for entertainment purposes, for example, this Muppet Show. I'm going to rerun it again with the music there. So this is something that you can have at home to cheer you up, especially if you have examination the next day, you know. So I'm going to conclude by talking a little bit about where the robotics I see it in the future. I explained to you guys in 1960s, 1960, robots have been used in many, many areas. We showed that robots in assembly lines. We explained that robots right now can be used in subway trains at good drivers. You can use robots in order to dig mine shafts. You can use robots to go into the nuclear cleanups and do some damage control. You can even use robots to do brain and bone surgery with a very good, great accuracy. So where do we go from here? And of course, new design and alternative ways to build the robots we showed you. One area in the design of the robots, I guess in future robots will become smaller and smaller. I think robots in future should become softer and softer, if especially you want robots to work with humans. Robots can become reconfigurable, like transformers. They can take different type of form and shape to do something. They can also replicate themselves. Wouldn't it be nice to have a robot that can say, well, okay, I want to go into that small area, but I cannot fit in there, so it starts to detach, you know, some part of its own body and put them together, make a small robot, baby robot, and says, no, you go there and come back and report to me. And after that, again, put it back. It would be ideal, and it would be very nice. We want the robots in the future to be more intelligent, to answer phone calls for us, to work with us. In doing that one, we have to make them become more independent in the changing environment. This is very, very challenging. We want them to make decisions and at the same time teach to themselves. And finally, it's very important in this aspect. Human body is so amazing that a 24 months baby can teach himself or herself to stand up and walk without falling down. We can actually browse through the whole crowd within a second. I can remove, say, 98% of irrelevant issues and locate people with familiar faces within a second. I can distinguish so easily between a shadow and a hole. The best robots in the best laboratories in the world still lacks this type of simple, and which we feel is simple, tasks. So there are many areas that we can work on that. The question of whether we want to use robots to have central intelligence or collective intelligence is something that remains for researchers to work. We definitely would like to have the robots to have some acceptance with people. We want the robot that we built to have a human feel comfortable to be around it. You don't want a scary looking robot. So ultimately, you want the robot to be at least acceptable response and response to your emotion and also learn from the emotion. So these are the things that we need our robots to learn. So the last transparency or role is that as future engineers and scientists or technologists, your role would be in any direction or any science that you pick up, first dream. You remember the whole concept of the robots came by Karl Čapek in a play, Workers, Artificial Workers, and Asimov. So that's the first thing that you need to do is to dream. In order to make your dream come true, you have to have a good plan and then go for it and execute it. But if you happen to work in the area of robotics, I'm hoping that you always remember the law 0 of the robot given by Asimov in 1950, 50 years ago. Whatever you do, try to build a robot that does not hurt or injure humanity. Okay, thank you very much.